we're going to extend the circuits concepts of power and energy into generalized signals today. Very often we want to know what the total energy in the signal is over time. That would be a measure, for example, of how much energy must be expended, say battery capacity to get some work done. Sometimes we're interested in power. Power, as you know, is the rate of energy. So that can tell us something about the average rate of energy being output or input to a system. So let's take these concepts from the circuit side and show how we adapt them into the general signals approach. So if we talk about signal and power in the resistive sense, as in power and energy dissipated by a resistor, and this can also be extended to complex power, but we'll stick with resistive because that's all we need to derive the signals concepts of these. We have, first of all, concept of instantaneous power, and several ways to do this. V squared over R, I squared R, for example, voltage times current. But we'll use this model here. We're used to seeing voltage signals, so I'll use a current signal today. I squared R is one measure of power, one way to measure power. And here we have instantaneous current, constant resistance, and therefore we have instantaneous power. And if I want to know what the energy in a signal is, since power is the rate of energy, I can take the power signal and I can integrate it over some time period. And that's our resistive concept of energy. Now, when we generalize this, we might be using these signals in the resistive sense, but they could be current or voltage or other types of signals coming from sensors. They could be signals represented inside a digital processing system and so on. So we're going to generalize. And in the generalized model, we normalize resistance to 1, which is going to make it drop out of a lot of terms. And it actually makes the power definition the same regardless of a signal is a current or a voltage signal. So this is generalized and we really don't need the concept of resistance just to look at a signal itself and say in a signal's sense, what is its power? So now to take the instantaneous power of a signal, what we have left is the signal squared. Now the signal, so like we have I squared over from where we're starting from. But we are going to, since we're generalizing, we're going to allow signals to be complex numbers. So what I'm going to do here is I'm going to take the magnitude of the signal, and it's no longer necessarily a current or a voltage, it's just a signal. So I'm calling it X. We take the magnitude and we square it. If it's a real signal, just the square. And if it's a complex signal, I want to take the magnitude and square it to get the power in the signal sense. Now, there's as you know, if I take the magnitude of a vector squared, it is the same as the signal, the value itself, times the conjugate. So that's an equivalent way to calculate it. And if I have a complex signal, this will be an easier way. So now we see we're multiplying together. There are two complex numbers that are conjugates. So we're going to end up with something that has an angle of 0. The imaginary part will cancel out. And if I already have a complex number in polar or rectangular form, the second form on the right is going to be simpler than calculating the magnitude, which is a hypotenuse, so it has a square root, and then immediately squaring it again. So we'll skip that step and do this calculation for complex numbers. Also, when computer programs are operating on signals, if they're complex, this is the approach we would take because it's just a little bit less work, but they're equivalent and get us to the same answer. So that's our concept of power in the signal sense. Energy is going to be an integral, just as it was before, of the power. So I'll just put in this expression for power, but you could use any, including the conjugate expression. And we are going to integrate that over some time period. So we'll go from negative capital T to capital T, where T is the parameter there. And if I want to know the total energy of a signal, which is something we're often looking for, I would take the limit as T approaches infinity. So I end up with an integral from negative infinity to infinity over all time, and I end up with the total energy of the signal. Okay, so now, depending on the signal, that energy integral might be infinite. For something as simple as a DC value, very well behaved signal, the energy is infinite because we're adding it up over all time. So and for those signals, we would want to take a step back and we would want to look at the power, which for a DC signal is going to be the same at each instant t, but we want to develop a notion of average power. So like, let's say another signal of great interest, just a simple sinusoid that goes on for eternity with the same magnitude and frequency. If I want to calculate the energy of that, it's going to go to infinity because I square it, so I have a non-negative quantity that I'm integrating over all time. And the power is changing. So we introduce this concept of average power. And the average power concept, again, is going to be a limit where the interval we consider is the entire signal for all time. And the average of, as we know, power is the time rate of energy. So here is the time. We are going to divide by the time. And we take the integral from negative t halves to t halves. Why am I doing the division by 2 here? The reason I'm doing the division by 2 is because this is the interval over which we're taking the average. So the width of the integration has to be equal to what I'm dividing by here, because we're going to take the energy and we're going to divide it by time. So that's why we're setting the integral up this way. And like I said, we're taking the energy, so any expression for energy will work. If I have a complex signal, I will use the conjugates, but we're not really dealing too much with complex signals in this class. So most often we'll see this magnitude squared approach integrate over time. So that's the definition of average power, and it would work just fine for that sinusoid or that DC value on the right, or more complicated signals. And if a signal is periodic, I can make a simplification. So if I look at this average power, let's take a look at what's happening with this sinusoid over here. And if I take the average power as t approaches infinity, and I'm going over wider and wider intervals, here I get out to 1 cycle of the cosine. And as I expand it out, the average power is going to change a little bit, but by the time I get out to 2 complete cycles of the cosine, so here we have 2 complete cycles, the average power is going to be the same because I'm going to take that cosine and square it, and I have now twice as much energy because I have 2 cycles instead of 1 cycle, but I also have twice as much time, so the average power will be the same. And as I go toward infinity at wider and wider intervals, I'm always going to be adding the same amount of energy each time I add a period. So when the signal is periodic, we have a simplification. We can say you can go as small as the fundamental period, which we call T naught, and you can do the integral over that fundamental period of the energy to get the average power. Now, we can generalize this yet one step further. The way I've written out this integral is I have made it match my drawing right here. We're going out symmetrically from 0. However, this is a periodic function, so I could have equally taken that period from 0 to the fundamental period of the signal, or I could have gone from minus t0 up to 0. I could have taken that integral. In fact, any interval of length t0, of width t0, is going to work just fine for us. So depending on how the math works out, you might want to integrate from 0 to t0 on some functions. Other functions, it might be more convenient to use even symmetry and go from minus t0 over 2 to plus t0 over 2. So there's one more step in generalizing this that we can make. Again, we're going to have to take the average over a period. And this notation here means an integral over any interval that has width or time support of t0. So I could you go from minus t0 halves to t0 halves. I could go from 0 to t0. I could go from 5 times t0 to 6 times t0 is what this notation means. So it means when you evaluate it, you just need to go over one period, and that period can start anywhere. So these are our simplifications for periodic signals. Now, given an arbitrary signal, we can evaluate whether power and energy are finite and infinite. And we'll draw a little grid here. There seems like there might be 4 combinations, but some of them are going to be special cases. So power and energy. And is it finite or is it infinite? So let's consider the different combinations that we might have. So for our DC value and our sinusoid that go on forever, they will get infinite energy, but they are still well-behaved, useful real-world signals that have a finite average power. So we call those signals power signals. So then there's other types of signals that do have finite energy. So for example, if I have a signal that starts at 0 and then at some time jumps up to some value and then does an exponential decay, if I take an integral of the square of that, I get a finite amount of energy. And so I'm going to be over here in finite energy. And when I divide that finite amount of energy by larger and larger time in the average power integral here, the power is always going to vanish and go to 0 if the energy is finite in a signal. So those signals, like this decaying exponential that I have there, we call those energy signals. And specifically, the power is not merely finite, but the power is going to be 0 in this case. If the energy is finite, since you're dividing a finite energy by more and more time to evaluate the average power, the power is actually 0 in these cases. Okay, so we have 2 cases remaining now. First of all, would be the lower left value. This here is a contradiction. This will not happen. If I have finite energy, I have to divide the energy by more and more time to get power. So if I divide finite amount by a larger and larger amount, I am not going to end up with infinity. So that case can't happen. The final case can happen, and this would be not a physical symbol, signal, not physical. even the power goes to infinity. When you evaluate that integral, it diverges. So that's something that cannot quite exist in the real world. So we would have to look at our model. Maybe something's wrong with the model if we come up with something that we think has infinite power, or we have made a mistake with a limit. But the finite power cases, zero power with finite energy is a key case of interest. That's an energy signal. And a power signal is one that, even though the energy keeps increasing over time, there is an average amount of power. So that is the end of this lecture segment. The next video lecture segment is going to have some examples of applying this in a little more detail and taking a closer look at the power of a sinusoid.